previous video we explained when damping factor is equals to 1, okay, critical damping, and then we derive the final equation. If I didn't define explicitly, this is the final equation for case 1. Okay, so when you have a damping factor equals to 1, you use this equation. Okay, then you solve for things. And then in our case today, in this now, our damping factor is lesser than 1, and this is the general equation. Okay, you remember I was always doing with the general equation. So first you have to first sub in your damping factor, your damping factor into your general equation. Okay, and yeah, and then just take note that my damping factor over here is square. It's because it's always square. Okay, it's always square, but just that in the previous video, if you go and check back, actually I didn't put the square over here. Okay, I forgot. So it's a careless mistake, just to let you know. And then with this, let's start off with our video. We have a general equation. This is step 1. When you sub in your damping factor, okay, be it if the damping factor, be it that the damping factor itself or square of it is always lesser than 1. Okay, for example, if you take 0.99 is the damping factor, you square it, okay, you'll get still lesser than 1. You never reach 1 itself. Okay, unless you go infinity lah, but in this case, yeah. Anyway, so once you sub in this, you have changed the equation. Okay, what do I mean by you have changed the equation? First, this when your E comprises of this portion and this portion, correct? Okay, and previously in the case 1 video, when our general equation is this whole thing is 0, because then when this damping factor is equals to 1, this whole thing becomes to 0, right? And therefore we are left with this only. So therefore we don't care about this. And then we factorize this one out, and we have a plus, and we have a plus b e minus omega nt. So we essentially eliminated this portion. But in this case, we have values that is not 0. Therefore we have a certain equation over here. This also explains why we have two equations. If you add two exponentials together, you can actually they're actually multiplying. So this, and this is this. Okay. Another difference between this equation, this general equation, and when after you sub in your damping factor, okay, is that you actually flip the interior and you are including the I. What do I mean? Okay, what do I mean is that let's say you have a you know that then this whole thing will be negative, right? Because as I say, if this or this square is lesser than 1, okay, then this is our approach. So therefore this is definitely lesser than 1. Okay, this whole thing that we call it A. So when this minus this equals to A equals to minus A lah, okay? Yes. So we would write it as minus A first. So this whole thing is minus A. And square root minus A is a complex thing already. So therefore you have to introduce the I operator, and therefore you know that I is equals to negative 1, and therefore negative 1 not with A, it's negative A, right? So this is why, because I explained over here. And when you and as I say, this is minus A. So if you were to, in another sense, that if you were to bring the negative out, because this is negative A, right? If you were to, okay, this is negative A. If you were to bring the negative 1 out, you are bringing the negative of the A out to this section, right? Therefore, the interior itself will have to change convention. Okay, so this is why this is at first is like that, right? And then this is negative. However, when you bring this, when you somewhat bring this negative out of them, okay, because this whole thing will become negative. You don't want it to become negative, ma. So therefore you switch the convention, so it become okay. So and then you have a -1 dot with this whole thing. I hope you get what I mean. Okay, I hope that it clears up the doubts for equation 2. Okay, so this is the portion that is a little tricky. So you have to take note. This is the tricky part. Maybe I should label it as a tricky. And then you have your equation when you sub in your damping factor. Okay, so we have already cleared out when you sub in your damping factor. Now you get an equation which is a much difficult and troublesome things, because we have a huge lot of things to talk about, and therefore, yeah. So after you get this, you realize that your equation, after you sub in your damping factor, you realize that your equation has a common term. Okay, from your this portion over here, you can see your general equation, you have a common exponential term. And when you do it, you can actually factorize this dude out, and you have this equation. You keep everything the same. Okay, I didn't cheat your feeling. So after which, once you get this, you introduce Euler's formula. Okay, because you want to eventually solve in terms of cosine and sine. Now, hold on. You may wonder why you don't use this equation. Okay, if I use this equation, I can solve for whatever thing I want, right? However, don't forget you have a I. Okay, you have a complex I over here. You cannot do anything. You have to remove this I. So the only method to remove this I, as I say, we have to derive equation that has natural frequency and damping factor as a variable. Okay, so when you sub in these two things, you get answer. Okay, and then now you have I in this section, you cannot do any shit. So our method is to use Euler's formula. Euler's formula states that in these things, you have this equation, ej theta is equal to this equation. And this equation, if you remember, is from your math, okay, your Fourier series also. And then now this is you have to sub in WD is equals to 1 minus, so this means that this portion, okay, will become WD, okay, and it's given in your formula sheet over here. Okay, WD is equals to omega n 1 minus and with so once you introduce, this is only introduction, I mean introducing you Euler's formula, and then you sub WD equals to this one, and then Euler's formula. So they come together as a set. Okay, you buy one get one free, so you come as a set. So therefore, for this portion, ej theta, okay, this is ej theta. That is, I theta. Okay, this whole thing is WD. Okay, so therefore, we use this formula, and since there is a E minus I, this whole thing is theta. Okay, this whole thing is it's and if you don't know what I'm talking about, this is theta. So EI theta, okay. Maybe I should define explicitly. This is theta, and this is theta. That'll be clearer. And then once you sub this equation to this, and then this equation to this, you'll get four terms. Okay. This one still stay the same lah. Okay. However, a cosine, okay, cosine, so we're just multiplying a into this thing. So it's similarly to this case, okay. So nothing much cheating your feeling, it's just something in. It's a complicated issue, so I hope that yeah. So first thing first, this is a partial summarization. So you get your general equation, you sub in your damping factor, and then you factorize out the common terms, you get an exponential in there. Once you get exponential, you see something is wrong, you got an I, you got an I here. Make sure you go and clear away the Euler's formula, which is this dude over here. You use the Euler's formula, you have this equation over here. And then nonetheless, you also remember have to sub in WD is equals to, this is the damping natural frequency. And then you have this equation, as this thing. Okay, so it takes on the form, and this this form takes on somewhat this form. Hope you get what I mean. And therefore, now you have this equation already. You group them by cosine and sine. Okay, you group them by cosine and sine. So you know that a plus b cosine. Okay, there are cosine terms and there are sine terms. Okay, and therefore a plus b cosine blah and plus I a minus b blah blah. Okay, and then now comes a more complicated part. Okay, is a subbing issue. Okay, you have two subbing level. I mean, just I just stop lah. Assume a plus b. Assume this dude as p, and we assume this dude as q. Okay, so it's just saying that this after you apply your Euler's formula, you group them, and then you take a plus b and a minus b in terms of this p and q. Okay, and therefore you have p. We just change the thing only. We just change the term. Okay, q is these things. And hold on a while. I don't know why I got something. Okay, it should be this. It should be this. Okay, I don't know why I put that. But it should be this equation. A minus b is equals to q. A plus b is equals to p. The cosine and the sine are the same as the cosine and the sine over here. I didn't touch this. Okay, I didn't touch this thing. Okay, and finally we derive, not finally, but rather that with this we derive the formula in the formula sheet. Okay, so if the test asks you to derive a formula for the formula sheet, okay, so they call you dude, you go and fucking derive this dude. Okay, so this is how we do it. Summarize again. Okay, I think this video I'll just talk about how to derive until here. So you have a general equation. You sub in your damping factor. This is a general equation. Sub in damping factor. Once you get the damping factor, then you do a little bit with the complex issue, and then complex number issue, and then you just bring out the common term. After which you apply you introduce Euler's formula and the damping frequency. You just sub in. It's just more on subbing in. Okay, so once you sub this into this form, and then you group them up, and then you sub in again. You sub p and q, so you obtain this equation. It's a multi-level subbing. Okay, so I hope this won't complicate you, because this is a very complicated issue. If you are, I hope you get what I mean. So it's mainly simply just saying sub your damping factor inside, and the rest is sub a lot of stuff. Okay, sub it's just in terms of subbing only. That's all. But the key two issues are subbing the damping factor into general equation first, and then you solve your equation. Make sure there is no variables or weird stuff, and it should be linear. And in terms of natural frequency and damping factor, I mean not should be linear, but rather than it should be in terms of natural frequency and damping factor. Okay, and then I'll leave you here. And the next video I'll talk about how we derive the final equation. So for case 1, we derive the final equation that describes the critical damping as this equation, right? Now we're gonna describe how we derive until here. Okay, so I shall see you in the next video.